Okay, today we're going to continue solving some systems and talk about a new concept called linear dependence. So we're just going to continue from the same example we started with last time. So last time we had this example. And when we did this, we kind of solved it with touch and feel by just creating a before and after graph and discovering that anything on this circle kind of got projected onto a line. And we kind of just discovered that it's anything on the line y equals x that gets pushed down to this point. So the solution, this transformation, is given by the matrix 1 minus 1 minus 2, 2. And this kind of squashes everything onto this line. And we want, one way of viewing this particular system of equations is it's to ask, okay, what vectors, after you apply this transformation, get squashed or moved to the origin. So since the matrix is squashing, we're going to ask which vectors get squashed to the origin, and it's everything on this line. And that's at least a good intuition, but it's not good to be specific with the algebra. So what we want to focus on to do is to focus on solving these systems in a specific algebraic way. All right, so to solve this, what are we going to do? We're going to put this in the augmented form. And we're just going to continue like we do. We're going to identify the pivot. There's the pivot. All right. And now what we want to do is we want to zero that guy out. So normally we'd want to scale that 1, but since it's already scaled, we don't need to do that. But we do need to change that 2. So we get row 2 minus 2 times row 1. And when we change that up, what do we get? Minus 2 plus 2, 2 minus 2, 0 minus 0. And we get 1 minus 1, 0, 0, 0, 0. All right, so last time we discovered that this bottom row here, you kind of have this bottom row, you missed out on having an exact solution. But more explicitly, I want to emphasize the fact that we missed a pivot. So we perform this operation of row reducing using this first column, but we never did it using the second column. And this is going to be indicative of free choice. So how do we interpret this? We can interpret this final form as just x minus y equals 0, right? We're just taking the coefficients from the reduced augmented matrix. And of course, the second row just says 0 plus 0 equals 0. So we don't have anything bogus. And of course, we can solve this equation right here. And this gives us right away that x equals y, right? So that gives us the answer that we got to before, right here, that x equals y. Now that you may want to just stop there and say that's the solution, and that would be good in just a single dimension. But when we have higher dimensional systems, you're not going to be able to describe the solutions as easily as just x equals y or a simple equation. So we're going to take a minute to kind of view this in a different way that will generalize much better. So one thing I want to emphasize is to go back here and give another way to explain what this equation, or rather what this equation, the matrix equation, what is that equation actually doing? That equation also can be interpreted like this. So the matrix multiplication 1 minus 1 minus 2, 2 times xy. Right? You could multiply it out and come up with a single expression for the top and the bottom, but I want to emphasize one other way of emphasizing this is 1 minus 2x, the vector 1 minus 2 times x, plus the vector 1 minus 1, 2 times y. All right, and what the equation asks us to do is we want that to equal 0. We want 1 minus 2 times x plus minus 1, 2 times y to equal the 0 vector in this case. So this is another way of interpreting our question, and this is a more geometric way. And what's really nice about this is it very clearly uses the geometric vector form. You can interpret this as taking steps, x steps in the 1 minus 2 direction, and adding y steps in the minus 1, 2 direction. And you want to figure out how can you combine these two steps to get the 0 vector, to basically say you didn't move at all. How can you use these two vectors to say that you didn't move at all? Well, since these two vectors are quite explicitly opposites of each other, right? 1 minus 2 is exactly the opposite direction and exactly the opposite magnitude as minus 1, 2. We have to take the same number of x steps, which goes forward in the 1 minus 2 direction, is backwards. So under this guy, we get the x equals y. But I want to emphasize this geometric way of thinking because I want to express our solution that we got before, x equals y, in terms of the geometric vector form. So instead of just being happy with x equals y, let's go ahead and go back to our reduced form. We're going to go back up to here. And we're going to take this guy and we're going to create a geometric vector form. So how do we do that? Well, first we're going to remember that we chose this y to be free. Right? Because it missed a pivot, y is free. And so what we want to do is we want to express the vector xy in terms of other vectors. So how do we do that? Well, what we're going to do is we're going to take this equation and we're going to solve for x. So if we solve for x, we get y plus 0. And now for the free choice variables, you get to choose that. You just use the variable itself. And so this says x equals y and y equals y. In this sense, y is the choice. Okay, this is a bit of a mystery, but just give us a second. How can we interpret this? Well, we can write this as a vector. We can write this as 1, 1 times y plus 0, 0. There's an implicit 0 there. And so this says that the solution to our equation is x equals y. But remember that the line x equals y, you can write that in geometric vector form as the direction, which is 1, 1, plus a starting point, and you can take any number of steps in that 1, 1 direction. So that's the geometric form for the line x equals y, or y equals x. And sure enough, that's exactly what we get here. This is the same line. The only difference now is that we have a y instead of a t. So that t was just a placeholder to say you can take any number of steps. In this case, the y is also saying you can take any number of steps, but when we indicate with y, that means that is the value of y. The only way to change y is to take y steps. We'll do another example later to indicate that with higher dimensions. But let's take a minute to kind of explore kind of this geometric vector form and this particular problem. What happened? What allowed this problem to have it so that the line was a solution? So what we're going to do is we're going to go back to this particular interpretation. And we're going to talk about a concept called linear independence. Or dependence. So for these two particular vectors, we observed that they were equal and opposite of each other. And in fact, you may notice that you can write this vector as -1 times the other one. So the reason why we had a problem, or maybe not a problem, but we ended up with many multiple solutions. Why did we end up with a free variable was because, in part because these vectors that make up the columns of our encoded matrix are not linearly independent. They are dependent on one another. So let's formalize what this is. So you are linearly independent if you can actually write one vector as a combination of all the others. So these vectors, you might have v1, v2, and v3, rather, if you cannot write them. Right? So for example, you might have v1 equals some multiple of v2 plus some multiple of v3, and this would mean that you are not linearly independent. Right? Because you can write it. If you can't do this, then you're linearly independent. Right? So when we go back up to here, this is an example of linear dependence. You can write one in terms of the other vectors. In this case, we only have one other vectors. So maybe a key point is you're going to be linearly independent. Two vectors are going to be linearly dependent if they're multiples of each other. Or put another way, they have a common ratio among their terms. So the common ratio here would be -1. And if you go back and look at what's really happening when you solve these linear systems, the reduced echelon form that you arrive to is secretly and kind of mysteriously encoding which vectors are independent of which other ones. So in the end, we discover that, hey, okay, y was dependent on x. It's just a multiple of that. So that's why we ended up with a free choice. In more complicated scenarios, some of the vectors are going to be independent of the previous ones and some of them aren't. So let's dive into that. Let's do a more complicated example. So this is another system. And we're going to just solve this, and we're going to express the solution in geometric vector form. So beforehand, we got a line. This time, just to foreshadow ahead, we're not going to end up with a line. We're going to end up with something else. And it's because these solution sets can be more complicated. They're not always lines, that we need the geometric vector form to express them. So let's just go ahead and get started. So this one, we're going to put this one in the augmented form. All right, and we're just going to reduce it, and we're going to put it in the row echelon form. Just as a reminder, the row echelon form is as close to the identity matrix as we can. Right? On the left side, we don't have a square matrix on the left side of this augmented matrix, so we're not even going to be able to get the identity matrix, but we can certainly try. All right, so what we're going to do is we're going to identify a pivot position, and normally the first thing we would do is scale it, but that's already done. We'd scale it so it would be 1. Right. Then what we're going to do is we're going to zero out all the other rows below and beneath it. And we can do that simultaneously. So beforehand, I haven't done this simultaneously. We can do this simultaneously. So for each of these, we're going to take that row and subtract a multiple of the pivot row. And the same thing for row 3. And just for emphasis, this 3 right here, these 2 and this 3 come from those entries right there. If you scale the row first, you're always going to be able to use exactly that entry there. You don't have to puzzle it out. All right, so what do we get when we do that? Well, on top, the top's not going to change. And the second one, we're going to get 2 minus 2, 2 minus 2, 4 minus 2, minus 1 minus 2, and 2 minus 2. 3 minus 3, 3 minus 3, 5 minus 3, 0 minus 3, and 3 minus 3. All right, so now what do we get after that? We get 1, 0, 0, 1, 0, 0, 1, 2, 2, 1 minus 3 minus 3, and 1, 0, 0. Okay, so notice now we've we got our one pivot, we got our one where we want it, and we got our zeros below it. Now something interesting has happened. This may be something we haven't necessarily encountered before explicitly, but you'll notice that where we would want the next pivot position, where we would want the next one, isn't there. And worse, there's no other one in that column to do. So this is a case where we have to skip on to the next row. So we're going to use this pivot position. Now, one thing I'm going to point out, notice that we missed a pivot right here. We're missing a pivot in that second position. And you'll notice, if we go back up to the original matrix, when I talked about pivot positions kind of encode which ones are free and which ones are not, well, you'll notice that these two columns are in fact multiples of each other. In fact, they're the same, but they are multiples of each other. They're 1 times each other. And this means that we don't actually need, right? We don't need one of those rows to kind of help us solve one of those columns to help us solve the equation, or in other words, it's going to be a free choice at the end. So the fact that we're skipping over that one was strongly indicated by the fact that the second column was simply a multiple of the first. All right. So now we're going to skip that pivot position and we're going to go there. Now we're going to scale that one. So we need to scale that one by half. And now we're going to zero out the one right below it. So we're going to use the current row minus that entry times the pivot row. And you'll notice that you immediately get zeros on the bottom. And now we can actually go ahead and do the top row as well. If you get good at these, you can do them both at the same time after you scale. So we can do that one too. And what do we end up with? We're going to end up with, nope, that's not a 1. That is 1 minus 3 halves and 1 minus 0. Or rather, 1 plus 3 halves. And all together, if we simplify this, we're going to end up with 1, 1, 0, 5 halves, 1, 0, 0, 1, minus 3 halves, 0, and zeros on the bottom. Okay, and we're done. This is the reduced echelon form. This is as good as we can get, right? We got our pivots right here, and below them and above them, we have ones, and there are zeros above and below, and to the left of all the ones, there are zeros. Right? This is as good as we can get. We have this nice little staircase pattern with the ones, like that. There's our staircase. It may not look as complete as the identity matrix we want, but this is as good as we can get. This encodes the solution to our system of equations. Now you may notice we skipped over a couple pivots. We skipped over this one and we skipped over the last one. And so what that's going to indicate is our solution is going to be dependent on those variables. So if we go back and translate back which variables are which, oops, that's not right. Right. This says that our x and our z are in fact going to be the ones that dictate the solution in much the same way that the y was free in the previous example. X and Z are going to be free choices here. All right, so to do that, we're going to translate this back into variables. So the first equation says W plus X plus 5/2 Z is equal to 1. And the second equation, or the second row, says that Y minus 3/2 Z is equal to 0. And now we're going to solve for the ones that aren't free. So we're going to solve for the ones that aren't free, the ones that are leading. So we're going to solve for W. So in this case, W is equal to 1 minus X minus 5/2. And Y is equal to 0 minus 3/2 Z. And now we want to put this into a vector form, right? So this is kind of the solution. This is as good as we can get. But we want to put this in a geometric vector form. So we need to know what X and Z are. So X is X. You get to choose what it is, right? So you're going to put an X there. That just says, since you get to choose what it is, or it's free to be anything that's possible, right? You're just going to put a single X there. This seems kind of weird and magical, but allows us to express the solution in geometric vector form. All right, and now we have Z. Well, Z's, sorry, not Z. Sorry. This is, yeah, Z is Z. Yep. That one's free too. All right, and now you'll notice that, okay, if we think of this giant system of equations, that's just a vector. Well, now we have our starting point. There's your starting point. If everything is 0, if all the free stuff is 0, if X and Z are 0, what do W and Y have to be? Well, they have to be 1 for W and 0, 0, 0 for X, Y, and Z. And then if you want a 1 in the X entry, what has to happen? Well, that means you have, oops, let's do this more explicitly. This means there's a minus there. So if you want to choose an X, you have to choose this vector. And likewise for Z, you have to choose this one. So any solution in your system of equations can be expressed like this. And to put this in vector forms, we're just going to distribute or factor out the X here. And we'll end up with 1, 0, 0, 0 plus minus 1, 1, 0, 0 times X plus minus, there's a Z here that's missing, 5/2 0 minus 3/2 1 times Z. And so this should look very familiar. This describes a plane. So a plane, remember, is a two-dimensional geometric object that has two directions in it, right? It's two dimensions because it's two directionally. So here, this plane lives in a four-dimensional space, rather, but it still has two principal directions you can go, and it has a starting point. And every solution to this system of equations that we started with can be described like this. Before we end, I just want to point out, we had X and Z as our free variables. And so if we go back, you may say, okay, well, when I pointed out at the beginning that the second column was exactly a multiple of the first, well, that's not exactly evident here, right? That's not exactly evident for that last column. Now, this says that since that's free, we should be able to take some multiple of 1, 2, 3 plus some other multiple of 1, 4, 5 and then end up with 1 minus 1 and 0. So the question is what multiples do you need there? It's not evident, it's not clear what it is, but it is possible, and that's why that one ends up as a free variable. All right, that's it for today.